Okay, I would like to thank Andrea, Diego, and Michele, that I don't see here, for the invitation to give this talk. Then, you see, every day if you open archive, you will see somebody has a dark matter candidate, okay? Then, for the time that I have, it's impossible to mention every candidate that people propose. Not only that, people make a lot of mechanisms and many things. Then you had the opportunity to have the lecture by Laura to learn about the different ideas for dark matter. But in this talk, I will actually focus on what we call theories. No? Then the goal is the following. I will try to do the following. I will focus on the theories that we have for physics beyond the standard model, where you can actually make a prediction. Okay, you have a dark matter candidate as a prediction. Okay, if you are in this talk, I hope that you believe that there is no a candidate in the standard model of particle physics, and you believe that it's hard to imagine cosmology without dark matter. If you know, I think the door is still open. Okay, but this is the goal. I will try to walk and tell you which are the theory for physics beyond the standard model where you can actually make a prediction, okay? And I will try to be very, very clear what I mean by that. Then, you cannot give this talk without talking about one of the main ideas that we have for physics beyond the standard model that has been there for a long time, and probably pretty sure you know, and probably you know a lot. And one of the ideas that has been there for a long time is supersymmetry. Okay? Then in the first part of this talk, I will tell you why people were so optimistic about SUSY dark matter or supersymmetry, and why people today are a little bit depressed. Okay? Then we will go from the simple things about supersymmetry to depression. However, there is no need to be depressed because only the experiment can tell us what is true. Okay? The rest are just ideas and speculation. Okay? Then, if you are not very familiar with supersymmetry, I cannot really teach you supersymmetry, but I will tell you a little bit about the main things why people believe for a long time that SUSY is something serious. No? I have to say there are a lot of things beautiful about supersymmetry, but I will try to give you mention what is really key. You know, when you write the minimal supersymmetric standard model, you find that the Higgs mass, you can predict the upper bound on the Higgs mass at 3 level, which is 91 GeV, the Z mass. There is an upper bound. At the time, we didn't know what the Higgs mass was. But the nice thing about this is that, you can compute one loop correction and try to achieve the 125 that we have today. Today, there are issues I will not mention about that, but the important thing is that SUSY is a well-defined theory that tells you how to predict the Higgs mass, but the prediction is up to the supersymmetric spectrum, right? SUSY predicts that every field in the standard model has a partner. We didn't see so far these partners. They had to be heavy because they are collider bounds. And the prediction, is up to the SUSY spectrum. However, it's a really beautiful idea for many, many other reasons. But again, this is one of the main reasons why most of the people believe that supersymmetry was something relevant. Then when you go to supersymmetry, you write what we call the superpotential. You write the Yukawa coupling. These are superfields and the mu term. And, you can do pretty much, you reproduce the standard model plus many other predictions. And at the same time, if you keep going and use the gauge symmetry of the standard model, you realize that you can write more terms in the superpotential. In particular, the terms in blue, they break lepton number and baryon number, the term in red. And I would like to remind you that in the standard model of particle physics, these two symmetries are accidental global symmetry at the classical level. They are broken by SO2 instantons. And you can actually show that B minus L is a good symmetry. Okay? It's also conserved by instantons. But again, the superpotential has the general, in general, should have all the terms. Okay? Then people didn't like the fact that if you combine these two terms, you will get proton decay at 3 level. We call this dimension 4 operators or contribution to proton decay. The lifetime of the proton, the bounds are so amazing that you really need to assume that naively that the multiplication of this coupling has to be around 10 to the minus 25 if the SUSY spectrum is around a TB. There are some details, but this is enough. The bottom line is that this coupling has to be very, very small. You know, all these couplings are protected by B minus L or baryon electron number. Then there is actually nothing wrong about having these terms there. But now, regarding dark matter, which is the topic here, people invented the symmetry that is called matter parity. It's defined like that. That is -1 for any superfield for quarks and leptons, and +1 for any Higgs or vector superfield. And if you impose this symmetry, these terms are not allowed, and you realize that you can have dark matter in the theory. Okay? And that's what maybe you saw for a long time. We call this actually SUSY dark matter because, as I will explain now, in the supersymmetric spectrum has many actually candidates for the dark matter. Okay? However, I have to say that, you know, it's important that young people understand that every time that there is a strong statement, it's good to go back and see what people are assuming. You have to impose by hand the symmetry and forbid these terms to get dark matter, okay? Then when we talk about theories for dark matter, okay, it's not clear this is a prediction without assuming extra stuff, okay? In particular, actually, I investigate for a long time the origin of this symmetry, and hoping that we could actually build mechanisms to understand the conservation of this symmetry. And typically what you find is that the simple mechanisms tell you that the symmetry should be spontaneously broken without baryon number violation, only electron number violation, and then there is no dark matter, neutralino dark matter, but the theory, you know, there is no proton decay, okay? I have to say that even if there is R parity violation, you could have other dark matter candidates I will not mention unless somebody asks me. Okay? Then how that works for dark matter? Then assuming that symmetry, in supersymmetry, you know, the gauge boson associated to hypercharge has a partner we call Bino. The neutral component of the W has a partner called Wino, and we have the Higgsinus, no? Then you can define, after symmetry breaking, something that we call neutralino. It's a linear combination of these guys. Then the neutralino can have 4 different personalities, okay? Depends on how they mix. And if this symmetry was imposed, the lightless one, this guy, can be actually stable, it's neutral, and you can follow Laura lecture, you can do a calculation and show how to get the Rayleigh density for neutralino and understand the predictions, okay? But as I said, the key point here is that you write a theory, supersymmetry standard model for other theoretical reasons or phenomenological reasons, but to get dark matter, you have to impose this by hand, okay? Now, you can, as you saw in your lectures, you can compute the annihilation cross-section for a given dark matter candidate. You can use the standard freestyle, use the standard formula to compute the Rayleigh density for freestyle, and you have to make sure that you don't overclose the universe and you certify the cosmological bounds for dark matter, right? Then, one big issue that has supersymmetry is that we don't know how the symmetry is broken. Means that unless you assume something very specific, we don't know what is the spectrum for supersymmetric particles, then the theory has a lot of free parameters, unless you assume some particular SUSY breaking mechanism, okay? However, people are very serious about this, And they study, you see, neutralino doesn't want to be their mother. They study all the annihilation cross-section, you see. It's a very rich theory because has the neutralino, has the superpartner that have electric charge are called charginos, and there are all the superpartner of the color fields and many, many things. There are other Higgses, but in principle, you can put all of them together, understand the annihilation of this Lilas neutralino in the theory, and do a calculation, assuming something about the supersymmetric spectrum, and show when you can actually get the Rayleigh density, okay? This particular calculation by this group is assuming what they call phenomenological MSSA. They assume like there are 19 free parameters, and they do a full scan of all these parameters to see when you get the Rayleigh density. And you can see often you can overclose, and cosmology tells you should be close to this line or below. Today we have many collider bounds. Then, for example, this gray area is excluded by collider bounds. But you know, you have a lot of scenarios where you can have, you know, the neutralino can be a dark matter candidate. And you can compute you can check the direct detection bounds and see if you're in agreement with them and do a lot of things, okay? But see that the neutralino mass is always, you know, below a few TeV, okay? Then if you take seriously this idea, the neutralino dark matter, you know, you will see that there is a chance that you see some of the superpartners at collider, and maybe you can discover supersymmetry, okay? The only problem is that people have been looking for that for a long time, okay? And so far we didn't see anything. But you know, it's not so easy to make a discovery. Then I will show you, I will not show you too many collider papers. This is a particular collider analysis where this is a neutralino mass. This is the stop mass. The stop is the superpartner of the top quark. You produce the stop, you know, it's just a QCD production. The stop decay to a top and a neutralino. Neutralino is stable, it's missing energy. And you try to reconstruct and look very well for this, a collider. If you don't see something, taking into account all the channels, you can rule out a large parameter space. You can see here that, you know, all the way to 1.2 TeV, of course, depends a lot on what is the neutralino mass. You don't see anything at collider, and then you are pushing and pushing the parameter space to heavy regions, okay? Again, there is nothing wrong with that. I have to say there are other theoretical issues that I don't want to mention unless you ask me. But as a theory, if you assume matter parity conservation, you can have a dark matter candidate. And this is why you see hundreds and hundreds of SUSY papers, especially experimentally. It's because people took this idea very, very serious, okay? However, I don't want to talk about collider physics. If I go back and ask this question, is that theory a theory for dark matter? This is not really clear because you're imposing by hand symmetry just to get a dark matter candidate. Could be that symmetry is there, but generically, the most generic thing that you get is that in the superpotential, you have this lepton and baryon number violating interactions, and they actually allow the neutralino to decay, and decay so fast that clearly cannot be a dark matter candidate, okay? But again, this is one of the main ideas that we have in physics beyond the standard model, has been there for a long time. Maybe, you know, tomorrow we will open archive and we'll see a paper say they found a superpartner. Maybe, who knows? But people are getting more depressed and depressed because you're pushing the spectrum to regions where, you know, you need to let's say, play with the parameters to achieve what you want, okay? Then it's maybe not so, but we don't really know. Only the experiment can tell us, okay? But let me emphasize again, for me, the fact that you have to put by hand the symmetry doesn't really tell me this is a good theory for dark matter because I am creating the dark matter candidate. It's not a prediction, okay? Then what I will talk today is something that I have been working with my collaborators, Mark Weiss from Caltech, my student Clara Murgin from CERN, my graduate students Case Wester, and experimental person John Butterwood from University College London. Basically, I will try to give you an idea that how maybe you can build theories that can actually predict a dark matter candidate without you making your dark matter candidate, okay? Again, there is nothing wrong to do phenomenological studies of many dark matter candidates, but if we ask ourselves, is this a theory for dark matter? It's not clear because you're making, you're cooking yourself. The theory is not making a prediction, okay? One example maybe that you could think about, imagine you go back in time before the top quark was discovered. The standard model of particle physics is anomaly free. It's a fantastic theory where all the anomalies are canceled. For all the anomalies are canceled per family. If you remove the top quark, because you didn't know the top quark was there is no way that you can cancel the anomaly. Then at that time, you could make the argument, something should be there. You don't know the mass because the standard model doesn't predict the masses, but you should find a fermion that we call today a top quark that allow you to cancel all the anomalies for the third family, okay? This is what is a good prediction. Some theoretical consistency that tell you should find something, okay? There are many examples in particle physics I don't want really to mention, but that is more or less the bottom line. You don't supposed to tell the theory what to do, okay? You write the theory for whatever you want and try to get the prediction from the theory, okay? If not, you can call yourself dark matter because you're making everything with your hands, okay? Okay, it's not fair. Then the question is, what kind of theory you could write down that can give you a dark matter candidate, okay? Then every time that you want to ask a question like that, you should go back to very basic things. You go to the standard model of particle physics, and you ask the question, okay, what is wrong with the standard model? Well, one thing that doesn't really work is that neutrinos are massive. We know that. Maybe you don't like massive neutrinos, but they're massive. And you need a mechanism to explain neutrino masses. The standard model doesn't provide the mechanism. Then this is a very pragmatic approach, okay? You can build whatever mechanism you want, okay? But you have to do that. And maybe one day we will know that. The Higgs was discovered. We understand how the electroweak symmetry is broken. We know how to give mass to all the charge fermions in the standard model. But this doesn't do the job for the neutrinos, okay? Then this is what I want to talk about is that let's see what happens when you try to write the theory for neutrino masses. Let's see if there are some possibilities that actually allow you to predict the dark matter candidate, okay? Imagine you can do that. Imagine you ask only the question, how do I generate neutrino masses? You write down whatever mechanism, and without expecting, you get the dark matter candidate. This is a prediction, okay? Because you didn't make the theory to get dark matter. You were thinking just about neutrino masses, okay? Then neutrinos are massive, and the masses are very tiny, below the EV scale. We don't know the spectrum, can be in normal order or inverted order. We have no idea. The good thing, the experimental input that we have is that their masses are really tiny, far away from the other masses in the standard model. Then better, you have a mechanism that maybe at least tell you a little bit about that. Then we don't know if there are Majorana fermions. They don't have electric charge. Or maybe there are Dirac fermions, okay? But what we know is that there is a symmetry in the standard model, total electron number, that is accidental symmetry at the classical level, broken by SO2 instantons. When this symmetry is broken by two units, you typically should get Majorana neutrinos. When this symmetry is conserved, broken in such way that you never generate Majorana neutrinos, You can ask me about that later. For that, you need extra degree of freedoms, right-handed neutrinos. Here, not necessarily you need right-handed neutrinos. There are many other possibilities. But the symmetry that tells you what kind of neutrinos we have in nature is a total lepton number. Okay, from neutrino oscillation, we know that the lepton number for a given family is not a symmetry, cannot be a symmetry. But the total lepton number could be a symmetry or not. Okay? Then if you go to this community, you will realize that there are a lot of mechanisms, from type 1, 2, 3 to infinity, okay? And there are many theories where you use many appealing ideas. For example, ideas like Patti Salan that was proposed actually here in Italy a long time ago, and many theories where you can actually have one of these mechanisms inside the theory to predict or to at least achieve the neutrino masses, okay? Now, what I will do is something actually way simpler than most of these things, no? As I told you, lepton number is a symmetry, accidental global symmetry in the standard model, and you can ask a very simple question. You can ask the question, can I write a theory for neutrino masses where this symmetry is just a local symmetry, as the other symmetry in the standard model, okay? Just a very simple question. Then this exercise is interesting because lepton number is not anomaly free in the standard model. And as I said, you want the mechanism for neutrino masses, but the first thing that you will face is that this symmetry is not anomaly free in the standard model. Therefore, you have to work to see how you define a simple theory where this symmetry can be local, and then you do a spontaneous symmetry breaking as you do in the standard model for the rest of the symmetry. Therefore, a very necessary condition is that you have to make sure that this theory is anomaly free, and then you do a spontaneous symmetry breaking, as in the standard model, okay? I don't want to change anything. The standard model is real, then follow the standard model. Nothing weird, okay? Something very simple. Then the interesting thing is that when you do this exercise, you realize that at least in all the simplest models that we found, that are in agreement with cosmology and any collider bound, anything that we know, you typically get a dark matter candidate. And this is a little bit like the example that I mentioned about the top quark, right? Because again, if you go to the standard model, you say you remove the top quark, there is no way you can cast an anomaly for the third generation, right? Here, what I said is my approach is very simple. You say, I want neutrino masses, and I want a spontaneous symmetry breaking using the simplest symmetry possible. Okay? Just lepton number. And when I do that, and I need to cancel anomaly, you find that typically you will get the dark matter candidate. This is a bonus, a prediction, or anything how you want to call, but it's a nice surprise because you start thinking about neutrino masses and not dark matter. Okay? I will show you how that works. Of course, you have to make sure that everything is consistent with cosmology. And I will talk mainly about Majorana and neutrinos because I am in Italy. Dirac was British, I am not in England. Then I think I am fine with that. Then if this is the case, what we call the seesaw mechanism, the scale for seesaw mechanism I will show you has to be low. Okay? Then typically there is a misunderstanding in the community that any mechanism that you have for neutrino mass, the scale has to be very large. I will show you this is not the case. Okay? But this is the bottom line, in analogy with what I mentioned about the standard model. How that works? Okay, you go back to graduate school, you check, you take the leptons, this is 3 copies of this guy, and you check all the anomalies, and you very fast realize that their anomalies are not 0. And the question is, how do you cancel this anomaly? And you get a simple solution where you can be in agreement with cosmology, you satisfy all collider bounds, and you don't make a mess. You don't supposed to make a mess in the standard model. Okay? You don't supposed to do something weird to the standard model, okay? The standard model works very well. Then don't do anything that will spoil the property, let's say, of the Higgs, for example, okay? Then when you do this, you find that there are actually kind of three simple solutions to that. I will explain this one here, and I will mention what I call a minimal thing, because it's the theory that has the minimal degree of freedoms to achieve anomaly cancellation, and you also get dark matter, okay? In all these solutions that we found for a while, you always get a dark matter candidate. Then you never know what model will be, if realized, but the important thing is that looks like, doesn't matter how you cancel the anomaly, you typically get a dark matter candidate, okay? Then how that works, you go back again, the standard model tells you that there are 3 copies of charged electrons. Then the first solution, which is not a minimal, it's absolutely not a minimal, but it's easy maybe to understand, is that, we have chiral families in the standard model, and here what you can do, you can add what we call Bertholli electrons under the standard model gauge symmetry. Then you see the quantum numbers are the same of the standard model, it's just that they can have different electron numbers, okay? And anomaly cancellation is constraining that this L1, L2 is -3, okay? This, as I said, is not the simplest solution, but the standard model fields, they have well-defined quantum numbers. Here, these Bertholli electrons have the same quantum numbers on the standard model. It's just the electron number could be different, okay? In particular, I will show you what happens when you have the relation that L1 equal to -2. Now, if you look at this, you realize that there are 2 fields that they don't have electric charge. They're a singlet of everything, they don't have electric charge. But there is now a new gauge boson associated to electron number. They will feel that force, okay? Then, if for any reason these neutral fields are actually stable automatically, you can have a dark matter candidate, okay? Then, how that works, the first thing is, as I said, the theory is anomaly free, and now you have to make sure that in a simple way they can be massive. You break the symmetry, and you don't make a mess, and they can get a symmetry in a simple way when extra Higgs, which are electron number 3. And this 3 is peculiar because in the standard model of particle physics, electron number is broken in 3 units by SO2 instantons. Then you can check the fact that you want to cancel anomaly and generate masses, automatically this Higgs should have electron number 3, okay? And you have the CISO, right-hand neutrinos are crucial here to cancel the Curie anomalies, and therefore you have the extra Higgs if you want the Majorana neutrinos, okay? And this is not the minimal thing that you can do, but it's a simple solution where these extra fermions have exactly the same quantum numbers as the electron in the standard model, okay? This is a little bit conservative, even if you don't want to find a simpler solution. I will show you the simpler solution later. Then, regarding dark matter, I will come to that, but as I said, any Chi-L or Chi-R combination is stable. But regarding neutrino masses, the right-hand neutrino mass is now related to the mass of the new gauge boson in the theory here. And then if you show that this symmetry breaking scale cannot be too high, the mechanism for neutrino masses is happening at the low scale. Then here you open the possibility that there is maybe a hope to test the mechanism for neutrino masses because everything is happening at the low scale. Now, regarding neutrino dark matter, as I said, in the case of Majorana neutrinos, Majorana dark matter, if you take just the Chi-L, doesn't matter which one you take, you realize that there are many channels, still less than supersymmetry, of course, for the annihilation of the dark matter, right? Then mainly you will have annihilation to leptons and right-handed neutrinos, the new gauge boson, the new Higgs, and then you can do what you saw in your lectures. You can do the standard freestyle calculation and get the Rayleigh density. Okay? Then, if you want to be in agreement with cosmology and don't have so much Rayleigh density, you find something interesting is that the symmetry breaking scale typically has to be below multi-TeV. 10 TeV depends how far you want to go in the perturbativity of the coupling, but you have to be at the lowest scale. When I say lowest scale is that if you read any paper about neutrino masses and seesaw mechanics, often people tell you that it's very natural to have a mechanism 10 to the 14 GeV. It's so natural that you never will test that. And therefore, the nice thing here is that, again, you just try to do something very simple. Try to get a symmetry of the standard model. You are not even making a symmetry yourself, okay? And you say, I want that symmetry to be gauged because I know that if this symmetry is broken into units, I get Majorana neutrinos or maybe Dirac neutrinos. When you do that, anomaly cancellation tell you I have a dark matter candidate, and therefore cosmology tell me, hey, the symmetry breaking scale should not be too large, okay? And that is why there is a connection between neutrino masses and so on. I will not bother with that, but as you can check, it's very simple to satisfy the direct detection bounds and be consistent with the experiment. I also don't want to talk too much about other aspects of the model, but I just wanted to mention that you have some lectures about the axion. This theory is actually predicting a pseudo-Boston boson that behaves like axion, also behave like what we call a majoron, decay to photons or neutrinos. You can study constraint big band nucleosynthesis, and you get a very interesting connection. Okay. Now, it's just a single pseudo Boston boson that only couple at 3 level with the neutrinos, is suppressed by neutrino masses. But he also coupled to the new fermions needed for anomaly cancellation. Then one loop, since you know exactly what fermions you have there to cancel anomaly, you can compute the coupling to photons. No, because you had two Higgses breaking lepton number. Then if you check the scalar potential, there are two global symmetries, and when you break, you still have one global symmetry that is broken by actually dimension 5 operator that actually give mass to this pseudo-Boston boson. We could talk more details later. Now, as I said, this is not the minimum model. The minimum model should be, typically every time that you try to write a theory and try to speculate, even if you get something that doesn't look like the standard model, here regarding the quantum numbers, it's always good to prove, theoretically, that you can cancel all these anomalies with the minimum number of fields. And apart from the right-handed neutrinos, you can actually add 4 fields. But again, you always have, there is no QCD quantum number here because we are talking only about, let's say, new leptons. You always find that there is a neutral field here that is automatically stable. Then, again, you play with all this and try to find solutions. It's always very interesting that you find, always you find a dark matter candidate in the theory. And I call this a prediction because, again, this is something like in textbooks. You go back to the standard model. You have the gauge, the local symmetry, and 2 global symmetry, lepton number and baryon number. And the experiment tells you, please do something for neutrino masses. Then before, do whatever, of course you can put fields by hand and build many mechanisms. There is nothing wrong with that. But before, one thing that you can do, it's not the only possibility, is to take the total electron number is a local symmetry and study the spontaneous breaking of that symmetry. And as I said, again, when you do that, you have to cancel anomaly, and the solution tells you that there should be a dark matter candidate. And this stability of the dark matter is independent of, of putting by hand some extra symmetries, as I mentioned, the C2 symmetry that we saw in supersymmetry. Okay? Again, it's a little bit sad that we don't have so many experimental input in our community. We know that neutrinos are massive. We don't know the mechanism. We know that we should have dark matter, but we know nothing about dark matter. Nothing. That's why you see every day a paper about a dark matter candidate, because you can put, anybody can be, anything can be dark matter. Of course, this is a joke. There's, of course, some rules, not too many, but there are some rules. But the interesting thing here is that you try to write a theory for neutrino masses using the simplest symmetry that we have in the standard model. And you don't have to make up a symmetry. When you do this exercise, you find that there is a dark matter candidate. Okay? In this particular framework, the dark matter has interaction with the new Higgses and the new gauge boson associated to electron number that couples at 3 level with the leptons. They don't couple to quarks. And you can do the exercise to compute the Rayleigh density, but the bottom line is that you can write a pretty simple theory for neutrinos that predict dark matter, and as a gift, once you put the cosmological constraint, you realize that the mechanism for neutrino mass should be realized at the lowest scale. Then you get a gift, you get the dark matter candidate, and you get a gift regarding the stability, because the fact that the scale doesn't need to be 10 to the 14 GeV, has to be multi-TeV, there is a hope at least to produce this field in a collider. Okay? Any question about this? Now, if I want to keep beyond that, it's really hard, because I go back to the standard model again.
Maybe I have a question. So, what's the real motivation to gauge lepton number apart from having a dark matter candidate? What I'm seeing?
No, dark matter is not.
Mass?
Okay.
Okay, my ground is no mass. And what else?
Okay. The only motivation is the following. We know. Thank you for the question. No. Right. The question is the following. You need a mechanism for neutrino masses. There are many mechanisms and many theories for neutrino masses, right? And there are even more ambitious approaches like grand unified theory and many things, right? The only thing that I said here is that there is a class of theory for neutrino masses that if the total electron number, which is the symmetry of the standard model, I know that this is the key symmetry, and if you think about the spontaneous breaking of this symmetry, you find that in the process of writing down a theory for a spontaneous breaking of total electron number, you find as a gift that you have a dark matter candidate. Okay? Now, that is the only point I am making here. Okay? Now, if you want to cancel the anomalies, you can check that the right-handed neutrinos are very, very important in the process, okay? And therefore, clearly, the right-handed neutrinos are also part of the game. And then, but again, the only point is that in the large class of theory for neutrino masses that we have, actually, you never get the dark matter candidate, because in any grand unified theory, anything like that, I'm talking as a prediction, right? It's not I write SO10, I can do CISO in SO10, I never get anything, okay? Of course, I can do supersymmetry SO10, but then even to get R parity conservation, I had to choose my representation to to make sure that our parity is conserved at the low scale. But there's a lot of, again, this is the only point here, is that there is a class of theories using the same symmetry of the standard model where you want to understand the spontaneous breaking. You get neutrino masses as a gift, you get dark matter, and cosmology tells you that the theory should live at the low scale. Okay? Now, there is always any other possibility, absolutely. Now, to go beyond that and talk about a theory for dark matter is a bit, let's say, more speculative, right? Because, there are like many extensions of the standard model where, but if you check carefully for dark matter, you get because you put by hand. You do, you just put some C, a C2 or whatever version of a C2, and you get the dark matter candidate. Again, there is nothing wrong with that, like in SUSY. But, it's not clear this is a prediction. A prediction is something, it should be like a gift, something that you didn't expect. Okay? Now, when I am here and I want to go beyond, I ask myself, okay, maybe I don't want to go beyond the standard model and make up other symmetries. I can do something more, which has nothing to do with neutrino masses now, but at least I ask myself there are many ways to motivate that. Maybe you will like the motivation later. But I can ask myself if I can do the same with other symmetry in the standard model. Okay? The standard model doesn't have so many symmetries. But you have one that is called barrier number. Okay? And you ask yourself if you can do exactly the same, but just now barrier number is a local symmetry. Okay? And the reason, historically we found that in the opposite way, but you can, if you check the anomaly cancellation for barrier number, they're totally different, but it's interesting to see that you can actually do something similar. Then, again, if you want to do the same for barrier number, and again, this is a little bit less motivated because neutrino mass is not necessary in the game, but it's one of the other symmetries that the standard model has. Then you are curious, can I do the same with barrier number? Maybe it's good for, for the proton, for baryogenesis, for anything that you want, okay? Because it's a very important symmetry in cosmology, right? Then, if you do the same, you have the same problem that you have to cancel the anomaly, and the same solutions will give you a dark matter as a prediction. And this is actually cute, okay? How that works?
Can I ask you something?
Yeah.
So, baryon number, gauging baryon number seems to go in the wrong direction.
No, because depends on the scale where you're breaking, right?
No, sure, but it introduce certainly more problems than.
No, actually,
global.
No. Again, you can do in barrier number whatever you want, but as I said, the only thing that here you can be curious, it's very important for cosmology in general, no? Barrier number.
But not gauging.
No, you can put global, you can do absolutely. I just try to tell you that if I do the job for total lepton number. No, let me finish. And then I ask myself, can I do the same for barrier number? I'm just curious about studying the spontaneous breaking of barrier number because it's just a symmetry of the standard model. And because maybe this is different from what we see. Actually, you will be surprised. In 99% of the theories that we have for physics beyond the standard model, talking about supersymmetry, grand unified theory, many other things, these two symmetries are explicitly broken, most of the cases. And here, this is totally orthogonal to typically what you have in, again, more ambitious theories. And you just ask the question, can I gauge? It's highly not trivial because if you try to gauge, maybe you get proton decay. And the proton decay bounds will tell you that the scale has to be big. However, you will see that the proton is always stable. then for the first time you find that there is a theory that tells you that the proton is actually stable at any level of perturbation theory. Therefore, let me keep going, but this is one possibility, okay? Again, I don't want to, this is not a religion, okay? This is a very simple approach. The standard model has these two symmetries, and you want to understand if you can do the spontaneous breaking, okay? Then anomalies are totally different here because you have only quarks, okay? You have only quarks. And then if you check these papers, you will get the same type of solutions. But here I will show you, I don't know how much time I still have.
15 minutes at most.
Oh, that's good. No, it's enough for me to have even 10. And then if you want to do the same for barrier number, instead of showing you a more traditional solution for anomaly cancellation, you can see that you can cancel all the anomalies with these 4 fields, and you also have a dark matter candidate with a fractional barrier number. Okay? Then this is a good thing to prove that you can do in a very simple way. You can take barrier number, you can gauge, and you break and see what happens. Okay? If you do that, and you realize that the proton is not stable, and you will have a problem with cosmology, you're wasting your time. Right? Because, but at least you learn something. This is not the case. If you know, I will not give you this talk. Okay? Then, how that works? Well, you actually can give the mass when extra Higgs that have barrier number 3/2. Then you can check any type of interaction that you could write down with this extra field in the standard model, and you never can write anything that gives you proton decay. Okay? Therefore, this means that the scale for a spontaneous breaking of barrier number could be low. Okay? Of course, it will be nice if you get something better. It will be nice if you can actually prove that the scale has to be low. Okay? Now, I don't want to give you too many details because this is a school, but I don't like to, I like to be between, give you some details and give you the idea. Then, you can check, as in any theory, the whole spectrum of the theory. You have a new Higgs, you have the dark matter candidate, and so on. And again, anomaly cancellation is predicting a dark matter candidate when you cancel the anomalies. Then you have to check the fact that you don't get proton decay. This doesn't mean that maybe the scale cannot be so low for barrier number. But you check all the collider bounds. This is the gauge coupling associated to barrier number. This is the mass of the new gauge boson. And these are, a collection of collider bounds. And you can see that the scale where you break this symmetry could be actually pretty low. Okay? You can ask me why the experimentalists could not do a better job for that. It's actually pretty hard. But it's interesting that you can have the spontaneous breaking even at the low scale. Now,
So in this model, that number is actually conserved.
I only gauge barrier number. Lepton number, I don't even pay attention. However, in the papers, if you check the papers, you can do the same for lepton number automatically. Then you can gauge both of them, break at the low scale, you don't get proton decay, and you get the neutrino masses. I just, for teaching, to explain this, I prefer to split them because they are two different symmetry. But I always, in this, if you check the papers, we prove that you can gauge both of them and break both of them at the low scale, and proton is always stable. It's the first time that you have a theory that tells you that proton is always stable. Okay? Then, I don't know, there are people looking for proton decay. I don't know. Maybe I don't know, it's not clear. Who knows? Then, At least in the U.S., every time that you give a talk, you have to make a joke. Huh? I don't know if this is allowed here, but there is a new Higgs in the theory that actually behave in a very peculiar way. We call this kukuyu. It's just an insect that during the night emit a lot of light, and during the day want to sleep. No? And the reason is that this Higgs is actually can have a huge branching relation to photons. If it's light, of course, it's below the WW threshold, or can decay mainly to dark matter. Okay, and they are very interesting phenomenological properties. If you want to ask me later, but coming back to dark matter, as in the case of lepton number, the chi is stable. After symmetry breaking, you realize that there is an accidental C2 protecting this field. And then, as you can expect, you can do the same job for Rayleigh density. You study all the annihilation channels. This is not like SUSY. There are not so many free parameters, and you can actually do a full job without assuming so many things. It's a very, modest symmetry. And again, as I said, if you want to do the job for Rayleigh density, the symmetry breaking scale or the mass of the new gauge boson cannot be too heavy. In some scenarios, the collider can rule out some of the parameter space. But if you are in any place below on the blue line or below here, depends on the value of the gauge coupling, you can be in agreement with Rayleigh density, direct detection, and everything is okay. But again, the message that I want you to see is that, again, cosmology is constraining the fact that the symmetry breaking scale has to be low. Therefore, you could look for this collider and maybe test this idea. Maybe the idea is totally wrong and this is never realized, okay? We don't really know what is true. Only the standard model of particle physics and GR are true, okay? But it's peculiar here that you can actually do something so simple for the spontaneous breaking of these symmetries, okay? Now, direct detection, I don't know how much you saw in the school. In this case, you will have also interaction through the gauge boson, but this is a Majorana fermion, velocity suppressed, then there are no issues with that. You can study things like in the galaxy, if the dark matter is sitting around, can annihilate and give you a gamma line, and there are a lot of gamma ray telescopes doing that. And then you can compute this. These are quantum mechanical processes at one loop. Typically, if they're, for dark matter experts, if you tend to compute this in any model which is not anomaly free, good luck. Because this is one of the key issues, right? The whole theory gives you something and gives you annihilation cross-section to photons which are not velocity suppressed, even if this guy is Majorana. And this is something peculiar about the theory. Then you can actually do a calculation and check the experimental bounds for the gamma ray telescope. And you find that, CTA, for example, could get very close to the experimental bounds. And, it's a signature that also you didn't expect. You didn't expect to have a dark matter candidate. You didn't expect that the fermions that you have for anomaly cancellation also will allow you to generate gamma lines, which are, the cross-sections are not velocity suppressed, and can give you something that is close to the experiment. You don't expect, and then every time that you get something that you didn't expect, following a very simple idea, you want to study the spontaneous breaking of baryon number and see what happens, okay? You can, do a full job computing all the gamma lines and everything, but I will not give you so many details. And as I said before I finish, the good thing about this, at least for now, is that we have the Large Hadron Collider, where you are colliding protons. Then any theory which predicts new degree of freedoms that couple to quarks can be produced at the Large Hadron Collider. And then you can predict, a large number of events for these things, and maybe a high luminosity LHC you could see something, okay? Then I think I'm happy to finish on time. And there are a few things that I want you to remember from this talk. Only a few things. One is, again, if you think about dark matter, and you talk about a theory for dark matter, again, there is nothing wrong to do phenomenological analysis and so on. But from the large classes of dark matter candidate that you will see in any, Wikipedia, you can ask the question, can I write a theory that is predicting dark matter? It's a prediction. Something that you didn't expect, okay? The case of supersymmetry is not clear because they are put in by hand. One case that I forgot to mention, the action is also very popular. But again, I was very interested about the multi-TV scale. The Pechet-Quinn scale is very high. Then, even if you see the action to test in the mechanism how the Pechet-Quinn scale was broken, you have to go to the high scale, okay? Then, the other thing that I was trying to communicate is that when you go back to the standard model and ask how to study the origin of lepton number, you realize that the theory predicted dark matter from anomaly cancellation, and the cosmological bounds on Rayleigh density tell you that this symmetry has to be broken at the low scale. Lepton number is it's actually more motivated because, again, you want to study neutrino masses, and the symmetry that tell you what kind of masses you should get is lepton number. And you want to study spontaneous breaking. Already that is fascinating, at least for me, that you get the dark matter candidate. But I proved that you can do the same for barrier number. Actually, as I said, Andrea was asking, you can prove that you can actually gauge both of the symmetry at the same time, okay? And you get both symmetries broken spontaneously at the low scale. And as I said, anomaly cancellation is predicting the dark matter candidate because to do a spontaneous symmetry breaking, you have to have anomaly-free theory. If not, you don't know what you're doing, right? Then I mentioned very briefly gamma lines. This is interesting. And maybe the most interesting thing is that in the first case, you will have a theory for neutrino masses and dark matter. In the second case, you will have a theory that is predicting the proton stability and dark matter. And that can be actually interesting because in both cases, the symmetries are broken at the low scale and they could be tested in principle. Okay, thank you.
So the question is, can you get a dark matter candidate from the symmetry?
Could be. They can be a little bit more complicated, but yeah, could be. It's just that, again, when you do SUSY breaking, your first goal is to be able to have a relative spectrum for the super partners, right? And there are many cases. You have gauge mediation, SUGRA, many. But you could make a bit more complicated where, yeah, you have some super field that one of the components, but I would say it's not a prediction. You will have to put things, you have to arrange things in your hand. But yes, you could do that. But again, I mean, maybe Andrea has a comment. I don't know. Could be. Could be. Yeah. Mm-hmm. No, this is, when, this is like in the standard model. We cannot predict masses for any firm in the standard model, right? We just adjust couplings to reproduce the experiment. Here, okay, regarding the electron number, what you realize that if you want to cancel the anomaly, the right-hand neutrinos are very, very important because there is it's hard to cancel QB linear anomalies and many things. And there is a symmetry that allow you to break, to cancel the anomaly. And then the only thing that you can do is that you will have the degree of freedom to have a mechanism for neutrino masses. You cannot predict neutrino masses. However, the extra thing is that the fact that everybody is getting mass from the same symmetry breaking scale, and cosmology tells you that the scale cannot be too large, everybody is getting a scale mass from a low energy scale, a multi-TV. Then nobody is super heavy here. Then the seesaw mechanism has to be low scale multi-TV, okay, or below that. But you cannot predict any masses for anybody because we are not able to do that in the standard model. Okay.
So when you get the map and variant approximately, we also get a gauge both of them. So what's the different expectation of mass?
Thank you. For example, which one? Let's take maybe I was too quick in the baryon number case, for example. No? Once you want to achieve the right Rayleigh density, okay, you see this is the mass of the gauge boson associated to the baryon number. The annihilation, this guy is very important to give you the right cross section for the annihilation of the dark matter. And then you see that you can, this is a very peculiar region where there is a resonance, but let's say generically you want to live here, and you see you never go beyond 5 TV. Of course, you can increase the coupling and you go maybe all the way to 15 TV. Again, there is like a nice upper bound, the masses of this guy. The Large Hadron Collider doesn't put very strong bounds on these masses. Look, these are all the collider bounds. Then the answer to your question is, when I try to do the job for Rayleigh density, there is an upper bound on the mass of the new gauge boson to be in agreement with the Rayleigh density. And from the bottom, I had to check all the collider bounds. And you can see that this mass can be actually pretty light without assuming any small coupling, and you can be in agreement with cosmology. Then you live in this, let's say, from the electroweak scale to a multi-TV scale where the theory can describe physics without any problem, without violating any experimental bound. And
why is there that on the previous plot, you have that as very thin region?
oh, okay. Okay, what happens is that one of the challenges is that you can annihilate to 2 quarks through this, no? But then if the mass of the 2 times the mass of the dark matter is equal to the mass, you sit on the resonance, and then the cross section can be so large that easily you can satisfy the cosmological bounds on the Rayleigh density. And that's why, but let's say this is not a region that's very generic, because it's hard to imagine. That's why I say it's a bit more generic to be here or here, where you don't need a resonance to do the job of cosmology. But you have to show all the possibilities.
Okay, if there are no other questions,
Thank you.
again.